I wish to present you a simple tool to simulate wave propagation in different scenarios. This is a summary of my presentation. At first, a general description of the tool. Then I will talk about how to define sources, sensors and reflecting surfaces, show you some examples of use, describe the simulation method. At last, I will show you how simple is the code to run the simulations. This is a general tool to explore wave propagation in 2 dimensions. The question is, how can we let beginners to explore wave propagation in a very simple manner? Well, we developed a function to extract information from a picture. The picture has color-coded objects. Red points represent position and number of sources, green points represent sensors, and blank points represent reflected surfaces. Our function reads the image and runs the simulation, then returns the signals registered by the sensors that can be plotted. It is also possible to store the simulation in a video file. Here we can see 2 windows, in the left a MATLAB window and in the right a paintbrush window. We are drawing some points. Red points are sources and green points are sensors. Then we must save the picture and type simulate in MATLAB to run the simulation. Because the function returns the signals registered by the sensors, we can plot them. To modify the simulation, we can edit the picture. Here we are removing one sensor. And drawing a rectangle to represent a tube. Black points code reflected surfaces. We remove one side of the tube to make an open end and move the sensor to the closed end. Save the picture and type simulate. We can observe the reflection in the closed end and then a reflection on the open end with phase inversion. The picture can be modified again to run another simulation. Here we copy and paste a rectangle and put both tubes close together. We repeat the process to make a tube array. Save the picture and type simulate. We can observe the reflection in the closed end of the tubes, but almost no reflection is presented in the open end. We can invite students to answer why they think this happens, and let them explore the scenario, changing the distance of the source, the dimensions of the tubes, or any other parameter. The second example of use is a very different one. It obtains the impulse response of a spherical head. It is a cylindrical head, in fact, because it runs in 2 dimensions. The black circles represent the head, and the 2 green points are represented both ears. The red arc of a circle is the source. It similarly propagates waves as a point source located in the center of the circle. Here the center is outside the picture. In this case, we use an impulsive signal. We can observe the reflection and diffraction of the head. As the function returns the signals of both ears, we can plot the impulse responses. And because this information is available in MATLAB workspace, it is possible to compute whatever we want. For example, the fast Fourier transform to obtain the frequency response of both ears. We can invite students to modify the picture to add ear canals to the model and obtain the impulse response. Here's a new picture with some modifications. The reflection and diffraction patterns are quite similar, but the impulse responses and frequency responses of the new model are more complex. We can invite students again to try different dimensions of the ear canals or different shapes of the head, oval one, for example. The third example is a very different one. Here you can observe the reflection patterns of the Schroeder's diffuser. The picture has a section of the diffuser and 37 green points in a semicircle, each one 5 degrees apart. The red line represents a plane source. In this case, we use a sinusoidal signal. Only 3 cycles of the signal are used to observe the reflection pattern without interference. The function returns the registered signal of all the sensors. In this case, we compute the mean energy of the reflected waves and plot them in a polar diagram. The case-based pseudospectral method is used to resolve the differential equations of wave propagation. It is based on the Fourier collocation method. Instead of the finite element method, it has no numerical dispersion for a homogeneous medium. This makes it possible to use impulse or arbitrary signal sources. K-Wave is an open-source MATLAB toolbox that implements the case-based pseudospectral method. It has been developed 10 years ago by Bradley Trively, Ben Cox, and Girigeiros. K-Wave is commonly used in biomedical ultrasound applications. We decided to use a very limited subset of the functionality of K-Wave for simplicity. The position and shape of sources, sensors, and reflecting surfaces are defined by a picture. Reflecting surfaces are considered as regions where velocity equals 0 to solve the differential equations. Simulation is coded in a simple script with 3 sections. 1. Parameters used, such as the speed of sound. 2. Calls the function that reads the image. 3. Plot the results. Here we show a complete code needed to run a simulation. The first section sets the initial parameters: the image file name, the scale in meters, the duration in seconds, a logical variable to choose if a video file is desired, the speed of sound, a technical parameter that states if the source pressure must be used in additive or Dirichlet modes, and the mathematical definition of the source. In this example, it consists of the sum of 2 sinusoidals with different frequencies. The second section calls our function. In this example, the variable sensor data returns the registered signal of all the sensors. When this function is running, we can observe the simulation in the display. And finally, the third section used to plot the results. The plot diagram of the source shows the superposition of the 2 sinusoidal. The high-frequency component is attenuated in both registered signals, but the reduction is more important in the first sensors located near the obstacle. In summary, simulations are designed by a picture and very few lines of code. This lets beginner students explore wave propagation. Advanced students can be able to analyze our function and create modifications to get more complex simulation situations. Our function is open source and is available with examples of use following the links shown or using the QR code. Thanks.